There is a hammer in a valley in England that has not stopped moving for 400 years. Not the same hammer, the same motion, the same water, the same forge. The river that drives it has been driving it since 1590. The iron that goes in comes out the same way it has always come out, shaped by impact, shaped by heat, shaped by the judgment of a man standing close enough to the metal to feel it on his face. The factory built 2 miles downstream produces steel by the ton. The forge produces steel by the inch. The forge's steel is better. Not by sentiment, by measurement. Iron has been worked by human hands for approximately 3,000 years. The transition from bronze to iron as the dominant metal of human civilization happened not because iron is inherently superior to bronze in its raw state. Bronze, an alloy of copper and tin, is actually easier to cast and work than iron. It resists corrosion better. It holds an edge adequately. Iron displaced bronze for one reason. Copper and tin deposits are geographically rare. Iron ore is everywhere. A civilization that mastered iron could arm its soldiers and tool its farmers from local deposits. A civilization dependent on bronze was dependent on trade routes that enemies could cut. Iron was not better, iron was available. But making iron useful required a technology that bronze did not. A bloomery furnace hot enough to reduce iron ore to a workable mass, and a hammer heavy enough and fast enough to work that mass while it was still hot. The hand hammer of the early ironworker gave way as production demands increased to a powered hammer. Water-powered trip hammers appear in the European archaeological record by the 12th century. A wheel turned by a river drove a cam that lifted a hammer and released it. The hammer fell by gravity. The force of water replaced the force of a man's arms. The judgment of where to place the iron and when to move it remained entirely with the man at the forge. That combination, mechanical force directed by human knowledge, is what the water-powered forge represented. And it is what the factory replaced with something that was faster and larger, but not, in every application, better. A master smith named Robert Shorthouse worked the Abbeydale Industrial Hamlet forge in Sheffield from 1847 to 1891. Abbeydale was already old when Shorthouse arrived. The water-powered forge on that site had been documented since 1685. The grinding hull beside it had been in operation since the late 16th century. By the time Shorthouse took his position at the tilt hammer, the forge had been producing edge tools, scythes, sickles, agricultural blades for 200 years. Shorthouse worked the same hammer his predecessor had worked. The same water wheel drove it. The same river drove the wheel. His job was to take a billet of blister steel bar iron that had been packed in charcoal and heated for days until carbon diffused into its surface, producing a high-carbon steel with a characteristic blistered surface, and work it under the hammer into a scythe blade. Here is what that demanded. The billet went into the forge fire, a coal fire burning in a stone hearth driven by bellows connected to the water wheel. The smith watched the color of the metal as it heated, not the temperature on a gauge, the color. Black iron heated to red, red deepened to orange, orange brightened to yellow, yellow approached white. Each color corresponded to a specific temperature range at which the metal behaved differently under the hammer. Too cold and it did not move. Too hot and it burned. The carbon oxidized out of the surface, and the steel became iron again, soft and useless. The working window, the range of color between too cold and too hot, lasted perhaps 30 seconds for a piece of the size Shorthouse was working. He had 30 seconds to move the billet from the fire to the hammer, position it correctly, and work it through the first sequence of blows before the metal dropped below working temperature. Then back to the fire, then back to the hammer. A scythe blade required between 15 and 20 heats. Each heat was 30 seconds of work. Each positioning of the metal under the hammer was a decision about where the next impact would fall and at what angle, shaping the blade's cross-section and curve according to the geometry Shorthouse carried in his eye. No drawing guided him, no jig held the work. The blade existed in his mind before it existed in the metal. He was making it visible. The crucible steel process, developed in Sheffield in the 1740s by a clockmaker named Benjamin Huntsman, produced steel of greater consistency than blister steel. Huntsman melted blister steel in sealed clay crucibles, allowing the carbon to distribute evenly through the melt. The resulting steel had uniform properties throughout its cross-section. Sheffield crucible steel became the standard for cutlery, springs, tools, and precision instruments across the industrializing world. But crucible steel still had to be worked. The forging, the shaping of the steel into its final form, still required heat and impact applied with judgment. The difference between a spring that lasted 20 years and a spring that cracked in the first season was not in the composition of the steel. It was in how the steel was worked. The grain structure of forged steel, the alignment of the metal's crystalline structure under repeated controlled impact, determined its fatigue resistance. A smith who worked steel correctly refined its grain. He moved the metal so that the crystalline structure aligned with the lines of stress the finished piece would experience in use. A blade's grain ran along its length. A spring's grain followed its curve. A machine that stamped or pressed steel to shape did not refine the grain. It moved the metal into position without aligning it. The difference was invisible to the eye. It was not invisible to the metal. Abbeydale Industrial Hamlet in Sheffield closed as a working forge in 1933. The water wheel still turns. The tilt hammer still falls. On demonstration days, a craftsman heats steel in the forge fire and works it under the hammer the way Robert Shorthouse worked it for 44 years. The hammer falls with the same force it fell with in 1590. The river drives it with the same water. The steel that comes out of it has the same grain structure it has always had. Sheffield still makes steel. The factories that produce it are among the most technically sophisticated in the world. Vacuum arc remelting, electroslag refining, computer-controlled rolling mills that maintain tolerances of fractions of a millimeter. But the specialty steel producers in Sheffield, the ones making surgical instruments, turbine blades, precision springs for aerospace applications, still specify forging over pressing for components where fatigue resistance is critical. Still specify the process that moves metal under impact rather than pressure. Still, in the most demanding applications, prefer what the hammer does to what the press does. The water hammer at Abbeydale is a museum exhibit. The principle it embodies is specified in aerospace engineering standards. The knowledge that Robert Shorthouse carried in his eye, the color of the metal, the angle of the blow, the sound of the hammer telling him whether the steel was moving correctly, that knowledge is gone. What it produced is still the standard. Sheffield is a city built on the sound of hammers. The Don River and its tributaries powered over 100 water forges at the industry's peak in the 18th century. The valley floors were lined with forge buildings, grinding hulls, cutlery workshops. The sound of the tilt hammers was the sound of the city working. Stand in the Abbeydale Valley today, and it is quiet except for the river. The forge buildings are preserved, the wheel turns, the hammer falls on demonstration days. The other 100 forges are gone. Some became industrial buildings for other purposes, some became housing, some are foundations under car parks and supermarkets. The rivers still run. The water that drove the hammers is still there. It just drives nothing now. Find Sheffield cutlery in your kitchen. Not modern Sheffield, old Sheffield, a carving knife with a handle worn smooth by a generation of hands before yours. A pair of scissors that has been in the family long enough that nobody remembers buying them. Look at the blade. If it was forged by hand, The surface has a character that ground and pressed steel does not have. A slight variation in the flat, not a defect, not wear, but the record of the hammer working the metal heat by heat. The grain of the steel running along the blade's length, aligned by a man who understood what alignment meant before the language of metallurgy existed to describe it. That knife will hold an edge longer than anything made after 1950. Not because the steel is different, because of what was done to it before it became a knife. The forge that made it is silent. The blade is still sharp. Is there an old Sheffield blade in your kitchen, a knife, a pair of scissors, a tool that has outlasted everything bought since? Tell me about it in the comments.